Hey everybody, this video lesson is going to cover balancing redox reactions. Reaction is one in which the electrons are exchanged between the reactants of the reaction, and oxidation states as a result change of those substances. The term redox comes from the two words reduction and oxidation. Reduction is a situation where an element or ion gains electrons and thus it loses charge or becomes more negative. Oxidation is when an electron is lost and then becomes more positive. And if something becomes more positive, it becomes less negative. When I think of oxidation or reduction, I like to think of the number line. And if an element is losing electrons, that means that it's gaining charge. And that means that the charge, if it starts at 0, becomes more positive or moves to the right. I think of the plus charge as oxidation. But if the substance gains electrons, then its charge becomes more negative, and that means the charge, if it were neutral, would move to the left on the number line. So if the charge increases, it's oxidation, and if the charge decreases, it's reduction. You can remember oxidation and reduction by this mnemonic, and the mnemonic is oil rig. That means oxidation is loss, reduction is gain. And when we're referring to loss and gain, we're referring to electrons in both cases. Now, redox reactions there are some that are quite simple, and there are some that are much more complex. Here's an example of a simple redox reaction, one where aluminum goes through a synthesis reaction to form aluminum oxide. Now, in order to identify what gets oxidized and what gets reduced, you first need to be able to identify the oxidation numbers or the oxidation states of each of your reactants. And there are some rules that we talked about in the past, but the rules are still in effect here. And the rules are basically, first, any element or diatomic molecule in its standard state is 0. So for aluminum, it's 0, and for each oxygen in diatomic oxygen are 0. Now on the product side, that is not the case, because aluminum is going to give away its electrons to oxygen, and oxygen is going to receive the electrons. So the substance that loses its electrons gets oxidized. So in this case, aluminum gets oxidized. And what is its oxidation number then once it turns from neutral to the product? So what you want to do actually is focus more on the oxygen. There are some rules in assigning oxidation numbers. First of all, anything that is charged, its oxidation number equals its charge. So for my two examples of oxidation and reduction of aluminum and oxygen, if you look at the oxygen, we know that its charge is -2 here, so its oxidation state is also -2. And that means that if oxygen is -2, in order for the charges or the oxidation numbers to balance, because that's another rule, that for all neutral molecules, the oxidation numbers add up to equal 0. So if that's the case, when I know that oxygen is -2 and there are 3 of them, then that equals -6. So if I have 2 aluminums, then each aluminum must be a +3, because I'm going to then multiply it by 2 to equal +6. And the +6 and the -6 have to cancel each other out, because this molecule overall is neutrally charged. Now for assigning oxidation numbers for atoms in covalent bonds, it's a little bit more difficult because you can't just look at the charge. You have to look at the charge that it would be if it were in an ionic situation. And oftentimes you look to the anion first, or the second element, and assign its oxidation number, and then assign the oxidation number for the first element in a covalent bond second. A couple of rules that are always the case is that oxygen is always a -2 oxidation number when it's in a covalent bond. And the same for hydrogen is always a +1. And fluorine is always a -1. And then the halogens, or group 17, are typically -1, but they could be also other oxidation states depending on what they're bonded with. But these 3 are always the case, and typically you'd be able to figure out the oxidation numbers of the other substances in the molecule or polyatomic ion if you knew these 3. These are rules for assigning oxidation numbers in a chemical reaction for the reactants and the products. But the next slide is going to show you some rules, and these rules are different. These are rules on how to balance redox reactions, and it's a little bit more complex than the example I gave you here today. this example balances itself. The electrons that are lost by the aluminum are picked up by the oxygen, and everything is easy peasy, neat, and square. But these other compounds and these other chemical reactions that I'm going to show you are not that easy. And it requires a particular balancing technique that I'm going to show you here on the next page. Let's talk about balancing redox reactions using a technique known as half reactions. And it's important to note that these balancing problems are all done in the presence of an acid or in acidic conditions. Here's a much more complicated redox reaction. Now what we have here is a bunch of ions. And the reason we have a bunch of ions is because this is a net ionic reaction, so we don't show the spectator ions in here. But we've got basically two polyatomic anions. This is manganate and this is chromate. And this is the manganese ion, and then this is just carbon dioxide. The first thing I'm going to do when I want to balance this redox reaction is that I want to split it into half reactions. And what that means is I've got two reactants, and I'm going to list them separately underneath. It appears as though I'm going to do these in separate order, one first and then the other, but in fact these two half reactions are happening at the same time. But I list them separately because it makes it easier for me to do the math. What I want to do is write down the manganese with the 4 oxygen, and I'm going to, on the product side, just write in anything that also has that manganese in it. And so I'm just basically taking this first one here and this first one on the product side, and that's one half reaction. Now the other half reaction is going to be anything that has carbon in it. So the C2O4 with the 2 minus, and then on this side is just the CO2. That chromate down a little bit so I have more room to work. So I've split the full reaction into two half reactions as you see in red. Now the second rule for doing this is start by balancing anything that's not hydrogen and oxygen. And I'm going to do this for each half reaction separately. So on the top one, the manganese containing half reaction, the manganese are already balanced, so I don't have to worry about balancing those. I'm going to save the oxygens later. Now the bottom one for the carbon, there's 2 over here, and then there's 1 carbon on the right, so I'm going to multiply that by 2. And I'm going to use maybe a black to do that. So 2 carbons in the carbon dioxide. Now I'm going to scroll up to give myself a little bit more room to jot in my rules. But underneath rule number 2, I'm going to then start balancing the oxygens and hydrogens. For this top reaction, I'm going to balance the oxygens by adding O to one side in the form of water. So on the product side of this manganese, I'm going to add 4 H2Os because that's going to add 4 O's to the product side of the manganese half reaction. Then to balance the hydrogens, I'm going to add hydrogens back to the left side or the reactant side of the manganese half reaction. So by adding 4 waters over here to the product side, I added 8 hydrogens to the formula, and then I'm going to come over here and add 8 H pluses as a result. And this is the reason why it's important to identify that these half reactions are happening in an acidic conditions, because the acidic conditions here are what supplies the 8 H pluses. So the last thing that I need to balance for this top half reaction is the charge. I need the charges, the overall charge on the reactant side, to be the same as the overall charge on the product side. And I do that by adding electrons on either the reactant side or the product side. And so let's take a look. I've got 8 plus charges and 1 negative charge. This whole thing is a -1 charge. So over here I have a total of 7 positive charges. And I'm going to make a little note down here. I'll erase it later, but I'm just going to make a little note to make sure that I keep my records properly. Keep the book, so to speak. Now on the right-hand side, I have just 2 positives, and that's it. So over here, I have 2 positives. Now I got to get these 2 numbers, these 2 sides of the half reaction, to equal one another. And the only way to do that is to basically bring this left-hand side down to 2 positive. And the only way to do that is to add 5 electrons then to this side. By adding 5 electrons, that takes this 7 positive down to a 2 positive. If you want to double check, you can. You say 5 negatives plus 1 negative is 6 negatives, plus 8 positives gives me 2 positives. So by adding 5 electrons to the reactant side, that brings my sides down to equal 2 positives. Now it's important to note that you can only add electrons to bring a high number down. You can't add anything to the side to bring a low number up to the other side. So we're adding electrons to bring the 7 down to a 2, not adding 5 protons to bring the 2 up to a 7, right? So that's the 1/2 reaction. Now I'm going to apply the same thing to the second half reaction. This time I may add some waters to balance the oxygens, and I may add some hydrogens to balance the hydrogens that I added from the water, but I have to take a closer look. So I've already balanced the carbons, there's 2 of each, and if I look closely at my total number of oxygens, I've got 2 oxygens times 2, or 4 oxygens on the right, and 4 oxygens on the left. So my oxygens are balanced, so I don't need to add any water. And if I don't add water, I don't add hydrogen either. So the only thing I really need to do in this problem is to balance the charge of this second half reaction by adding electrons. And so over here, I have a 2 minus, and over here, I have 0. So I need to bring the 0 down to the 2 minus. So on this side, I'm going to add 2 electrons to bring the 0 down. Remember, we're bringing the larger number down to equal the smaller number. In this case, the smaller number was already negative, so I need to bring the larger 0 down to negative by adding 2 electrons on this side. So I'm going to take the work we've done so far and put it down here beneath the rules to give myself more room to apply even more rules to what we've got going on here. So let's bring these 2 half reactions together, shall we? So I'm going to scroll up a little bit more and give myself even a bit more room. And I'm going to label this third rule number 3, again here on the bottom, giving myself space to get the job done. So the third rule is find the lowest common multiple of the electrons and multiply by an integer so that the electrons match. And so up on here, I have 5 electrons on this side and 2 electrons on this side, so lowest common multiple of 5 and 2 is 10. So I'm going to go ahead and multiply the entire half reaction to get the electrons to be 10. So I multiply this by 2 to make 10, multiply this by 2 to get 16, multiply this by 2 to get 2, multiply this by 2 to get 2, and this by 2 to get 8. So my coefficients are 2, 16, 2, 2, and 8 for the first half reaction. Now the next one, I need to multiply everything by 5 to get this to equal to 10. So multiply this by 5 to get 10, and this by 5 to get 5. Now that I've got my half reactions so that the electrons are equal to one another, now I can bring the half reactions back together again. So this is rule number 4. So once you're done, you add the 2 half reactions together. Half reactions together, I'm going to eliminate the like terms. And what that means is that I have 10 electrons on the left and 10 electrons on the right, so those eliminate one another. Now if I had waters on both left and right, and I don't, but if I had waters on the right side of this reaction and waters on the left side of this reaction, they'd cancel each other out and they'd reduce to their lowest amount. But since the only like term in these 2 half reactions is the electrons, it's the only one I have to worry about. So my final answer is 16 H pluses plus 2 MnO4 minus plus the 5 C2H4 2 minus is equal to the manganese 2 plus 10, it's 2 manganese plus the 10 CO2s plus the 8 H2Os over here. And now my final answer is the fully balanced redox reaction that includes H pluses because this is done in an acid and water because, of course, acids are all aqueous solutions. We're going to finish this video lesson off by doing one more example. I'll apply the same rules that I just showed you on the last slide on this new example. So what we've got is an As2O3 with NO3 minus, and it's combining to produce H3ASO4 and N2O3. So I'm going to first split this into 2 half reactions. I'm going to pull out the arsenic-containing compound from the reactant and also the arsenic-containing compound on the product side. So that's one half reaction, and the other half reaction is the nitrogen-containing compound on one side and the nitrogen-containing compound on the other. Making sure that I translate everything properly and making sure I include all of the charges as well. Now, as I mentioned before, you want to first start by balancing each half reaction and start with the things that aren't hydrogen or oxygen, so in this case arsenic. And I'm going to toss a 2 out in front to balance the 2 of the arsenic. Now in this arsenic one, I'm going to stay here and I'm going to balance the oxygens by adding water. So you want to do the water first, then the hydrogen second. I noticed that I have 4 oxygens, but it's multiplied by 2, or 8 oxygens on the right and only 3 on the left. So I'm going to add 5 oxygens in the form of water to the left-hand side so that I now have 8 oxygens on the left and 8 oxygens on the right. And then I'm going to look back and count my hydrogens on the left and right, and chances are if I added water on one side, I'm going to add hydrogen to the other side. And that's probably the case here. So I look and I see I have 5 times 2, or 10 hydrogen on the left, and 6 hydrogen on the right. So this side needs 4 more hydrogens in the form of H+. And finally, to this half reaction, I need to make sure that the charge is balanced. Over here on the reactant side, I have no charge, but on the product side, I have now added 4 positives, and now I need to add 4 electrons then to balance out the 4 positives that I just added. So that takes care of that half reaction. Now let's go down to the bottom half reaction. On the reactant side, I have 1 nitrogen. On the product side, I have 2. So I'm going to multiply this NO3 minus times 2. Now I want to balance my oxygens, and I look to see that I have 6 oxygens on the left, but only 3 on the right. So I'm going to add 3 oxygens in the form of water on the right-hand side so that the oxygens balance each other out. Now back to the left-hand side, I need to balance the hydrogens, so I'm going to add 6 hydrogens in response to the 3 waters that I just added. Finally, I want to take a look at the electrons. On this reactant side, I have 6 positives and 2 negatives, or an overall 4 plus charge. And on this side, I have a 0 charge because there's no ions at all. And so, as a result, I need to add 4 electrons to the reactant side of the second half reaction. When I do that, it brings the 4 plus down to a 0, and this side still remains 0. Finally, I need to combine the 2 reactions back together. And I'm going to do that in blue here. So, I find a lowest common multiple of my electrons. Well, it happens that they are exactly the same. So I don't need to multiply by an integer of either of these half reactions to get them to equal one another. They cancel each other out. But I also need to pay close attention to the other like terms. In the last one, the second half reaction didn't add any water or any hydrogen to it, but I wanted to pick out this one because you see that you have H plus on the product side of the first half reaction and H plus on the reactant side. And so we want to combine like terms. And so these 4 hydrogens are going to cancel out, and all but 2 of these hydrogens remain on the second half reaction. And you can do the same for water. I see that I have 5 water on the first half reaction and 3 water down here. So I'm going to cancel out all 3 of those water and reduce this 5 water down to 2 water. And everything on the reactant side. And we've got 2 waters, and we've got As2O3, so that's here. And I've got 2 hydrogens and a 2 NO3s, so that's those. There's 4 things to add up on the reactant side. On the product side, anything that didn't get canceled out remains 2 H3ASO4s and just the 1 N2O3, and everything should remain balanced. All the elements are balanced, all the charges are balanced, and I'm all finished. That takes care of this video lesson. Thanks for watching.